Hey, it is 2 p.m. CET, and I guess it's time to get started. Uh, Let me begin by wishing all of you a good morning, good afternoon, good evening, depending upon which part of the globe you're tuning in from. My name is Shrikant Joshi. I'm from University West, located in Trollhättan in Sweden. And I welcome you all to this, the second seminar in the METASIS webinar series. Incidentally, METASIS is a UKRI. For those of you unfamiliar, it is UK Research and Innovation funded program, which is supported by the Engineering and Physical Sciences Research Council, which is EPSRC in UK. This program is focused on advancing high temperature steam electrolysis and solid oxide energy systems for low carbon hydrogen production. The METASIS program is led by Robert Gordon University, and my co-coordinator for today's webinar, Professor Nadimul Faisal, is actively involved in this program. Uh, just for context, sometime back in December, Faisal received a travel grant, which was particularly aimed at enhancing Scottish Arctic connections. And as part of the activities associated with that grant that Faisal got, we thought we should dedicate one of the stops in this METASIS webinar series specifically to promote bridging UK Nordic research. And that is exactly what today's webinar is about. I will now hand this over to Faisal so that he can tell you more about this webinar series. Faisal?
Thank you, Professor Joshi. Let me introduce our four great speakers today. The first one will be from Professor Odne Burheim from NTNU, Norway. He'll be talking on the role of SOEC in turning trees and renewable into long-haul aviation fuel. The second one will be from Dr. Ashish Ganvir from University of Turku. I'll be talking about multi-material manufacturing for sustainable energy applications. The third one is Dr. Rafael Nakashima from DTU in Denmark, and he'll be talking about heat integration opportunity in solid oxide electrolysis. And the last one, but not least, Professor Ian Froitzheim from Chalmers. I was visiting him just last week. He'll be talking on interconnects for SOFC, SEC, and corrosion mechanism. So the plan is each presenter will be spending around 20 minutes time. After first two presentation, there will be a short break of few minutes, like up to 5 minutes. And then the last two presenters, and then there will be audience Q&A. So hopefully the session will end on time. So a little bit on housekeeping. All attendees are on mute. You can please use the chat function for any question. And we will take all Q&A at the end of the session. If there are any technical issue, please try to re-log in back again using the same link. The session is being recorded. It will be available on YouTube channel. So I will share the link later on. And also, hopefully we aim to finish on time. So without further delay, may I invite our first speaker, Professor Odne Burheim, to share his screen. Thank you.
Yeah, thank you. Just 1 second there. Very nice introduction. Okay. You now see.
Yes, we can
Does
see.
it make sense what you see, or is it like very broad? A bit strange.
We can.
Okay. It's all right.
At least on my screen out there, it's kind of elongated with your slide, just a small part of it. I don't know how others see it, Faisal.
Yeah, same here. Yeah, I think if you can.
I need to share it in a slightly different way because I have such a wide screen. Okay, so I do it like this, is it better now?
Yeah, it is better.
This is good. This is good. Yeah.
Can you see my cursor?
Yes.
Okay, that's very good. Okay, so thank you for inviting me for this. Today I wanted to talk a bit about the role of solid oxide electrolysis cells into a process called biomass to liquid. So the idea is if we take trees as part of a natural carbon cycle and we essentially burn them in an entrained gasifier with just a little bit of oxygen, then we can create the syngas. And so if we do that, then we can do Fischer-Tropsch afterwards, and then we have a bunch of, for example, kerosene that can be used for long-haul aviation. Some shortcomings in this process. It only uses about 40% of all the natural carbon cycle carbon. And solid oxide electrolysis have a couple of really good contributors into that. I also want to give acknowledgement. These are studies that have been going on for quite a few years on modeling level from my group and colleagues. So I'd like to acknowledge PhD students on the way, Dr. Anders Nelson, Mohammed Stadi, Gonzalo Alamo Serrano, Professor Magne Hillestad, colleague nearby, Professor Björn Austbø, as well as John Farrell. And it's also been a couple of students along the way on this, undergrads that have contributed also on published papers. So I would just like to say I'm very happy to have worked with them. Okay, so I want to say a little bit more about the motivation and outline for this. When we think about BTL, biomass to liquid, it is a process that has a very, very low greenhouse footprint. It's mainly in the production. And so when BTL is burned later on, it's considered carbon neutral because the carbon comes from natural carbon cycles. So compared to different other types of fuels, the BTL is a very promising carbon neutral fuel. It suffers from low carbon utilization. So I'll come back to that a bit later. The other thing I want to mention is 2% of global climate emissions stem from the aviation sector. So fighting CO2 emissions in the aviation sector isn't really that big. But I guess since decision makers have a lot of carbon guilt over traveling so much, we still care a lot about this. If we look into the aviation sector, I think 20% of the emission from the aviation sector is from flights that are less than 1,500 kilometers. So that's about the length of Norway. So sort of if you go from south of Norway to south of Italy, that's the type of distance we're talking. So this type of aviation doesn't really contribute that much, and it's also the only one that sort of can be electrified. But for the remaining sort of 1.5 to 2% of global emissions needs to be tackled by combustion and use of turbofans. So the BTL process, as I mentioned, it starts with biomass coming in, envisioned as forestry waste, essentially. It has a pre-treatment, which is essentially drying. It goes through an entrained gasifier, where wood chips together with pure oxygen under stoichiometry. So creates a syngas that then goes for a bit of cleaning. And then we have, by adding more steam, we sort of shift carbon monoxide into hydrogen and CO2. So because when we add steam, we also tie up more of the carbon that could potentially have been fuel as CO2, then the carbon usage or utilization is kind of low. So that's what where we think it's very good to add solid oxide electrolysis, and we have done a lot of modeling work around this. Further, one removes some water as well as some CO2, and then you do Fischer-Tropsch and you have products. So I have a simplified sort of sketch at the lower end of my slides, showing how you can take 100 units of energy in the biomass or 100 units of carbon, and out comes a little bit below 40% of the carbon in the fuel, and also just over half the energy that's embedded in the biomass. Okay. So now we talk about power BTL. So that's essentially when instead of feeding water into the water gas reactor, we're feeding hydrogen. And so then that becomes a reverse water gas shift reactor, and you can see that here. It goes through the same cleaning procedures, and it actually, because of the balance between carbon monoxide and hydrogen, makes sense to have 3 stages of Fischer-Tropsch, and that gives products. If we look at the carbon utilization, it sort of takes the carbon utilization from 38% to more than 90%. So we're utilizing much more of the carbon to have as in the fuel. And this relates to that we don't feed oxygen together with hydrogen into the water gas, but we feed only hydrogen, sort of shifting CO2 into carbon monoxide. The other thing one can see, because this also requires electric energy, so if we compare adding sort of 70 to 95 unit equivalents of electric energy, we sort of get almost 70 more units energy in the field in the fuel. So this kind of means that we have a very high conversion of electricity into e-fuels and e-SAF. And so in that way, we can sort of envision that we have wind farm collecting wind and sort of accelerating that through hydrogen, solid oxide electrolysis into a natural stream of CO2, giving us fuels that can provide aircraft propulsion. In doing this, we have done a little bit of modeling of the cell potential of solid oxides. We have also looked at heat integration. So if you preheat steam, and it's quite a lot of high heat temperature heat from the gasification, we can sort of envision lowering the cell potential of the solid electrolyzer, balancing out the ohmic losses, and therefore have very high energy efficiencies. And so if you consider sort of the wind to tank efficiency, that's almost 100%, and I think that makes this a very interesting process to pursue. So looking at the two processes, we sort of have these mass flow diagrams where you can see the BTL. Very little carbon comes out in the Fischer-Tropsch products compared to what we put in. But for the PBTL, we have a very high degree of the carbon utilized in the Fischer-Tropsch products. So what we thought we could maybe do to improve this further, if we look at the Fischer-Tropsch, it's quite a bit of sort of carbon monoxide, hydrogen, and very light hydrocarbons that comes out. In the carbon stream, this also presents a bit of energy. And so this is currently fed into the gasification reactor to get more syngas. But we wonder, what if we try to do something else about this? So then we come to a concept that we call fuel-assisted solid oxide electrolyzer, FASO-AC. So if carbon monoxide, hydrogen, methane, and ethane are fed to the anode of the solid oxide electrolysis, what's going to happen then? So if you think about hydrogen only, it would mean that you take hydrogen on water on the cathode sides, oxygen goes through, and because we feed hydrogen, it will just produce water. So it's essentially a hydrogen pump with oxygen going through, and this gives almost zero reversible potential. So carbon monoxide, hydrogen, and methane are experimentally verified to do the same thing. We have also done this with respect to understanding internal thermal gradients in the cells and the thermal balance, and it looks to go very well. We have a couple of papers around this. And what's also interesting to think about for many other processes with fuel-assisted solid oxide electrolysis cells is that you can take any fossil hydrocarbon and feed into the anode like this, and then produce hydrogen for very little electric energy because you have available chemical energy. The byproducts of this is really CO2 and water. And if you then cool and quench this, you can envision a very beneficial CCS process. Perhaps not the sequestration part, but certainly carbon capture. So when we look at this, the feeding the tail gas into the anode of the SOEC doesn't have that many beneficial energy effects, but it actually lowers the electric energy input need. So still, so it's making overall very high energy efficiency for this. But still, it's only utilizing 91% of the carbon, and we would like it to be more. Because it takes energy and resources to transport forestry material to such a site, and utilizing that carbon for making more fuel, we think would be beneficial. So, so that's what the FASO-EC is about. It's utilizing the residual tail gas better. The cost of such a system goes up because solid oxide cells have a cost. But when we look at the process for whether it's the fuel-assisted power BTL or just the power BTL, a lot of the carbon is lost in cleaning up the acid gas removal. So if we could separate CO2 from the acidic gas, which is mainly hydrogen sulfur, then we could recover even more carbon. And so we're talking about taking maybe 80% of the residual 9%, adding sort of another 7 points. And then we can sort of get this 91% utilization up to 98. And so this is an initial studies. It's currently under review. So we see a carbon efficiency going up a lot with this separation of CO2 and H2S. However, also the cost goes up. So it sort of becomes a question of how much are one willing to pay for this type of additional fuel. But it is a source of carbon neutral electro stuff, and I think that will become very important in the year ahead. How am I doing for time at this point?
Yeah, all good.
Okay, so I wanted to mention another example. So we started playing with fuel-assisted solid oxide electrolysis in this PTL system, but we're also curious, are there any other places where solid oxide electrolysis would be very beneficial, because it's the lowest energy consuming electrolysis that we currently have. So if we look at how manganese, for example, is made, it's made in a submerged arc furnace. So soften this talking into things, it can mean sustainable aviation fuel. On this slide, it means submerged arc furnace. Essentially, you have manganese oxide at a oxidation state of 4. You have carbon and electric power, and this goes into the arc furnace. And out you have a couple different gases, typically a lot of carbon monoxide together with CO2, and this is currently burned. And then you have your metal. So this is an industry that's kind of keen on improving. So what they did next was that they started pre-treating the manganese 4 with carbon monoxide as to get manganese 2, so MnO, going into the submerged arc furnace. It turns out that hydrogen does this several times faster. The hydrogen is a much better pre-oxidizing agent for manganese. Now, in this process, they still use carbon monoxide, but we're arguing that what if we take that carbon monoxide and feed into a solid oxide electrolysis cell as a fuel-assisted solid oxide electrolysis cell? Then we can make hydrogen that they can either sell or use for this pretreatment. So that's essentially what this study is about. Producing hydrogen from carbon monoxide, and these gases are also available at very high temperatures, so that's also good for this process. We found that larger plants benefit more from this, and preheating of steam is a bit important. And so if we look at the different cost of anodes, of electrolysis cells, so we assess sort of a price per square centimeter. It also matters a lot for how this sort of improves the economy of such systems. That we published a year ago, and that's sort of my introduction to what solid oxide cell systems can be used for in making sustainable aviation fuel, and also in the metallurgical industry. Thank you.
Thank you, Odne. Thank you very much for your presentation. So if you have got the audience, if you've got any question, feel free to put in the chat function. We'll be taking all Q&A toward the end. So may I invite Dr. Ashish Ganvir, the next speaker.
Hi, yes. So I'll share the screen. Do you hear me well?
Yes.
Very good, okay. So some unstable internet connection. So let's see if my 20 minutes, I don't have any interruption, but I just give you a heads up. So I'll share the presentation now.
Thank you.
Okay, so you'll be the timekeeper, right?
Yes.
I also have my own. Just a second.
I can see the screen. You can get started whenever you're ready.
Yeah. Okay. All right. Good afternoon, everyone. My name is Ashish Ganvir. I'm associate professor, tenure track in digital manufacturing at University of Turku in the Department of Mechanical and Materials Engineering. Hi, I'm co-leading a research group called Digital Manufacturing and Surface Engineering here at University of Turku. So today I will be talking about multi-material digital manufacturing for sustainable energy applications. And my research mainly focuses on how advanced manufacturing processes such as laser additive manufacturing and thermal spray can be used to fabricate structural as well as structural materials, but also functional coatings using either of these processes that I just mentioned. And in this talk, I'll be taking more of a manufacturing-centric perspective for this webinar's theme. And then I'll try to discuss how these advanced manufacturing technologies can actually help us bridge the gap between the advancement in the materials development to the actual systems that are manufactured at scale. Okay, so to begin with, this is quite evident, and that's why maybe we also have the theme that there is quite a lot of focus on, say, green and digital transition, especially in Europe, but also globally. And this is more like the need for the society. Now, if you look at how this whole chain works, so basically we have the systems that are used to produce energy. Then there is a storage of energy, and then obviously the use of energy. And I think, in my opinion, everywhere in all of these three sort of categories, um, it is important that all these three categories are addressed equally if we want this transition to really happen, right? So basically the production of energy, the storage of energy, and its utilization in various um, aspects in the industry and in society. Now, in everything, one key question that actually fascinates me is that how can we manufacture various materials and components that are required for the systems that are used in either of I mean, all of these three categories that I'm actually talking about: the production, storage, and utilization. So manufacturing, in my opinion, uh, is very important, which is also sort of triggering me to look at like what are the various challenges from the manufacturing point of view. Um, so it is also quite well known, especially to the community that is here listening to us, is that there is a lot of development during the last 5 to 10 years towards various systems used in production, storage, or in the utilization of these energy devices. So if we take an example in the on the first pillar, which is the production, we have SOEC, and there was a nice presentation just before this addressing that. But also solid oxide fuel cells. Then there are energy storage devices such as batteries, but also the use of this energy, such as the engines, where you sort of burn the green fuels like hydrogen and ammonia. And all of these are quite essential, as I explained in the previous slide. Now, if we look at most of this system, there is one thing that to me looks very common, and that is all of these devices are made out of multiple materials if you look at this as a whole system. And because of this multi-material architecture, the complexity is quite high. So if you take an example of say SOEC, so starting with the interconnect, then you have a oxygen electrode, solid electrolyte, fuel electrode, metal support, right? If you think about the solid state battery, you have the two metallic current collectors. Inside you have two different electrodes and also a solid electrolyte. When we talk about, say, engines where, say, hydrogen or ammonia is combusted, there is the structural turbine blade, one part of the engine, which is then typically coated with uh, uh, different types of coatings such as bond coating, support environmental barrier coating, thermal barrier coating. Now, all of these systems examples are each sort of layer, if we call it a layer or area, has a different material which brings its own requirements in terms of manufacturing, etc. So now, if you look more carefully, all of these devices, as I said, are inherently multi-material. In nature.
Ashish, you may want to close your video if that helps.
And
Ashish, you are there?
Faisal, maybe we should just wait a couple of minutes, if that's
Yes.
okay, for see if Ashish can reconnect.
Indeed.
And if it seems it's taking much longer, maybe we should just continue. With, is the next speaker here or
Yes, Rafael is around. Yeah.
around? Yeah.
Yes, I mean, you can. Should I start? What do you think? We can wait as well.
I think you can start now. There may be some network issue
Okay.
there.
I'll try to share my screen.
Thank you.
And let me see. And I think I'll be quite brief, but I have the tendency of talking too much. So I'm preparing myself to put few slides. And what I wanted to talk about with you, it's about heat integration on solid oxide electrolysis. And I feel that this is an important topic, and there are also some misconceptions around this topic. So my purpose on this short meeting is to go to the fundamentals, explaining what it is, the opportunity, and what we have seen so far from like some kind of recent studies that we conducted here in DTU, for instance, to give you a perspective. So what I have proposed, what I have kind of planned for today, as I mentioned to you, is divided into two parts. One, it's about the context of heat integration. That means like what is the thermodynamics, what the system looks like, and what is like key manufacturers are saying about this. And later, I will pair with some of our own studies to exemplify and also to explain what is the possibilities and limitations on this field, and finish with a message, which I hope it'll be a good message for you or not. So, all right. So what is the context of heat integration? So I found this very nice here graph from Topso to explain a little bit where is it coming like this, let's say, opportunities to use heat to produce hydrogen. So this comes from the thermodynamics. And if you see this graph here on the right, it's a graph of temperature versus like the enthalpy of formation change of the reaction, the hydrogen formation reaction. And it's this green line here. And you see something very interesting. You see that below 100 degrees, this value, which relates to the total energy demand, is much higher than the value that you have for higher temperatures. And the reason that it is because, at low temperatures, you have liquid water, and at higher temperatures have vapor water. And the difference between the liquid water and the vapor water, it's some energy that you can pay as heat, right? So it's this, let's say, dash area here. And this is a huge gain, like for instance, for SOEC, because suddenly, like this low temperature electrolysis, PEM, alkaline, they cannot escape from this, let's say, from these limits on thermodynamics. But for high temperature electrolysis, you can like pay this energy demand as steam. If you see like this graph a little bit further, you can see something more interesting. And is that the difference between this green line and this like kind of gray line here. And this gray line here is the Gibbs, let's say, formation of the reaction. So you cannot pay like less energy than this gray line here, because this is impossible by the thermodynamics. But in theory, you can pay this like as a minimum amount of energy to produce like a hydrogen. And you can imagine that the difference between this, let's say, green line and the gray line is an amount of energy that you can pay as high temperature heat. What it means is that, like depending on the voltage that you operate of the cell, you can have a regime where you have like thermoneutral, endothermal, or exothermal regimes. And in the endothermal regime, you can supply part of the energy as heat. But this is quite difficult because of the high temperature of this heat. But in theory, you could. So there are some gains that the SOEC is related specifically with the thermodynamics of high temperature production of hydrogen. The gains is like partially on the steam generation, and the other is in high temperature, let's say heat, if you are operating in the endothermic region. Of course, in reality, it's a bit more complicated because you don't have only cells, you have a whole system. So like, for instance, here, like on the left, you can see like this is a core, it's a demonstration core from Topso, and it comprises of the stacks and some of the BOP, some of the heat exchangers and heaters. And here I provide some kind of graphical illustration of what it looks more or less inside. And you can see that in order to provide the reactants, at the high temperature that this stack operates, you need to have both an electrical heating system as well as like a heat recovery system, because it's very difficult to supply heat at these high temperature levels here. So usually in the system design, what you do is that you provide this as electrical heating, not as like a heat from some other reaction or heat from some other process. And that means that once you analyze, the efficiency of the systems with, let's say, the load, it actually, which in the load here, you can imagine is the voltage, right? With the change of the voltage, change of the current, and you see something very funny. You see that what you would expect, for instance, from the stack, which is to increase, let's say, the efficiency, because you're operating on this, remember, this endothermic region here, right? That you're paying something not only on electricity, but you're paying in heat, let's say heat of the reactants. you would expect to have a higher, let's say, efficiency when you go for that region. But in reality, where you can you hear me? Is it okay?
Yeah, we can hear you.
Okay. When you see is in the system, actually, it's constant or even drops below. And the reason is because you are having to pay this heat energy anyways as electricity on this high temperature level here. So what it seems to be like let's say, at the advantage of the stack level, it becomes in the system electricity anyways, so you actually don't have this efficiency gain that you were thinking. So when we are saying like about heat integration, let's say on the electrolysis, solid oxide electrolysis system, most of the times we are actually referring to the steam integration, because this is much easier, let's say, to integrate in the process from like a different process of from a different reaction. You can integrate this much easier than you can integrate like high temperature heat. And chances are that if you're paying this indirectly as electricity, there is no gain on efficiency. So why bother to do it? So here I kind of compile some of the numbers provided by the main, let's say, manufacturers here in Europe and in the US. And you can see here names for like from Topsoil, Sunfire, Bloom Energy, and Fuel Cell Energy. And what is showing this graph is how much is the energy consumption of their systems. And this energy is divided into electricity and heat. And you can see that they more or less change like how much electricity or like how much heat in the sense of steam, but they kind of keep on the same level of total energy consumption, because this energy consumption is more or less related to the thermoneutral, let's say, voltage, the thermoneutral condition. So you see that most of the manufacturers cannot escape from the thermodynamics, let's say, of this problem, but they can design systems that take more electricity, this, for instance, to heat up the stack, heat the core, and have a better heat integration. So you reduce the steam consumption, or you try to minimize, let's say, the stack consumption, or try to minimize the consumptions of auxiliaries and pay more, let's say, heat. On average, what you see is that 14% of the energy consumption to produce the hydrogen can come from the steam, can come from the heat. So this can, of course, translate into savings of you in the hydrogen production if you have another process that provides this steam for you. And that's where I want to introduce some of these recent studies from DTU, in which we evaluated these, let's say, opportunities to integrate like this SOEC with the downstream process, and also what is the impact of this on the cost, the final cost of the hydrogen, to get a better sense of like what is the, let's say, the edge that we can have here with heat integration. And the first one that I want to showcase is like this work from Matthias, and he's in the audience. So hi, Matthias. I hope you're doing fine. And what we did here, and he did mostly, was to evaluate what is the potential of integrating ammonia production and hydrogen production from SOECs. So here you can see like a Sankey diagram where you see the energy, let's say, flows from electricity and heat from all the process. And you can see the ammonia synthesis is a very exothermal process. So you can actually recover some of this energy as heat through a heat exchanger network, and therefore like produce steam to provide to the SOEC. And this can see that you have minimized by doing so the amount of electrical heating that the whole system needs. What do that means is that you can see on this graph on the right here, you can see the difference between the isolated SOEC, an integrated SOEC, an isolated SOEC, and their efficiency curves with the different loads of the ammonia plant. And you can see that the difference between these, let's say, circles and the squares is how much you can gain on the efficiency by having the two processes working together. You can see that you're not only increasing like on the steady state and full load conditions, but you also increase during the partial load operation of the ammonia plant, because you can recover some of the losses of compression power, or like some losses of the ammonia, the heat from the ammonia synthesis, you can still use to like minimize the drawbacks, or let's say, of the partial load operation in the SOEC. Overall, the system will have like some efficiency penalties, but you can see that the SOEC has a huge like efficiency gain on doing so. More precisely, you can provide 4.5 kilowatts of heat per kilogram of hydrogen, and that refers to our case that we study to 70% of the steam generation. So two things that you can read, like you can read in a positive sense that you can produce a lot of the steam required to produce the hydrogen, but you can also see that even in the best case of the ammonia integration, you cannot get 100% of the heat from a downstream process. So that's also a huge misconception that sometimes you see, that they think that the steam will come from free. And as in some cases, depending on your design, you still will have to supply heat from electricity to provide the steam. So that gain is not like 100%. A second study that I want to highlight is a study done by Javed Bayrami, and he looked at to a lot of, let's say, different types of influence on the sensitivity of the hydrogen cost, from like a capacity factor to degradation to size of the modules and so on, to see what we can do to minimize the cost of hydrogen and get to the point of like €1 per kilogram. And you see here on this tornado, let's say, graph, that actually the steam availability, the amount that is the influence of heat integration, is one of the lowest actually that influences the cost of the hydrogen. And that should not come too much on a surprise if you were like paying attention, or like on the presentation, because you can estimate, let's say, how much is the impact of the cost of the heat in the hydrogen, if you know how much of the energy, let's say, cost is the proportion of the cost of energy and the cost of the hydrogen, and how much you can pay this energy as heat, right? So, for instance, we know from like thermodynamics that this, and the manufacturers, that the amount of energy that I can pay as heat is like 10 to 17% of the total energy required to produce the hydrogen. And if, for instance, if the energy is 55% of the cost of my hydrogen, then I have a range of like 7% of like, let's say, cost reduction, from the worst case of like completely paying on electricity to the best case scenario that I'm paying everything from an external process, right? And usually, because you have heat integration, because you have other players, this number will be even lower than 7, because you will recover some of the heat of in the system. So it can be like 3 to 4, or it can be higher if you have like a very expensive electricity system, and therefore increasing the proportion of the energy, let's say, influence on the levelized cost of hydrogen. So the message so far, you can see from like two angles. Like you can see the cup like half empty or half full. You can see like from the half empty side that heat integration alone will not drastically like reduce the hydrogen cost, will not be the panacea, or no, it will not be the reason that we have like $1 per kilogram hydrogen. And that's the pessimistic view, right? So, but the optimistic view is that, this also indicates that the technology, the SOEC technology, doesn't necessarily need to be close to, let's say, an ammonia plant. It doesn't necessarily need to be only when you have like a heat source available. It can actually be thrive even in the absence of this, because the influence of the heat, it's small compared to the other, like, let's say, parameters that we have evaluated so far. For instance, the cost of electricity. So that also opens, like, let's say, from the commercial side, like a lot of possibilities of seeing high temperature electrolysis, not only on ammonia plants, but also in SAF and methanol, where like actually heat is scarce, like as a surplus of this plant. Yes. And finally, I just want to highlight that we are like in the works of having like this IEA test, where we're having like some state-of-the-art reports. So stay tuned if you are like interested to see more about the electrolysis in comparison, and also specifically to the Danish case. And you can sign up for like some mail list by using this QR code, or just reaching out to me at the contact. And with that, I thank you all for the attention. I hope that didn't blow the time. I was not checking on doing. So thank you very much.
Many thanks, Rafael. Very impressive. A lot of things to absorb from your slides. So well done. So maybe we take a 2 minutes of break while, may I invite Ashish to get ready for his presentation. Ashish, do you want to try again?
Yes, I want to try again. Maybe from the beginning, since I was just at the start, right?
Yeah, maybe you can close your video. That may help with the bandwidth.
Let's do that. Yeah.
So while you set up, I just a couple of announcements from my side. We'll be having third session of METASIS 3 on 7th of April. So let me share that link with you all. If you are available, please register to that event. I'm putting that in chat function. So that is by Dr. Mark Bankhead. He'll be talking about nuclear to X. We have been collaborating with him. His interest is in how we can produce hydrogen from steam, and also thermochemical cycle molten salt electrolysis. So he'll be talking about some of the opportunities and challenges in that area. Additionally, we are also looking for speakers. We have speakers lined up until June. If anybody interested in to be a presenter in future sessions later this year, please drop the email. That will be great. And also, we can also use this opportunity to collaborate each other. Right. So, Ashish, do you want to start now?
Yeah, let's start. So I'll keep my video off, just to avoid second time the same problem, right?
Thank you.
Okay, good afternoon, everyone, once again, and my apology for this unstable internet connection. I really hope that this works this time. So my name is, once again, Ashish Ganvir. I'm Associate Professor, tenure track in Digital Manufacturing at University of Turku. I'm a part of Mechanical and Materials Engineering Department, and I co-lead a group called Digital Manufacturing and Surface Engineering, DMS. Today, I'll talk about multi-material digital manufacturing for sustainable energy applications. And my research mainly focuses on how advanced manufacturing processes, especially laser additive manufacturing and thermal spray, can be used to fabricate structural components, but also functional coatings for various applications. And nowadays, since last 4 or 5 years, particularly for energy applications. And in this talk, keeping the theme in mind, I'll take more manufacturing-centric perspective. And I will try to discuss how the two technologies that I actually research can actually help bridge the gap between, say, lab scale exploitation of these devices and to more of a scalable use for the society. All right, so now to begin with, I think this is quite well acknowledged thing that there is a strong transition happening within Europe and worldwide for green and digital aspects of the society, and that is also the reason that we have this kind of webinars. But when you look at this kind of transition, there are various pillars, in my opinion, which needs to be sort of focused, because it's not one thing, one sort of a problem. So you have naturally the energy production, but also you have the energy storage, as well as the utility of the energy. So for example, in industries or say EVs or any other applications, right? So all these three pillars are important if we would like the society to really transition to this green and digital theme. So now when we think about all of these three pillars, I call them pillars. So many of these energy system devices in either of these pillars are actually for sure have gotten a lot of attention during last 5-6 years. And there is a lot of rapid development happening. So be it SOEC, on which we already had the couple of talks, or SOFC, also batteries, more advanced batteries such as solid state or sodium based, for etc. And also say the green fuels such as hydrogen, ammonia, how they are actually used to create work or energy using engines, for example, right? So all of these aspects, there is one thing that is, in my opinion, that is common, is that most of these devices are quite complicated, or as in they are complex because there is a certain architecture and which is this multi-material. So for example, if you look at SOEC, you have a metallic interconnect, then you have three different functional layers, the electrodes, as well as electrolyte and the metal support. So this is one type of SOEC. I give an example. Similarly, if you look at solid state battery, there are two metal current collectors, and inside you have the active battery electrodes and also solid electrolyte. And then if you look more towards the third pillar, that is the utility side, we have this say engine, and I'm taking an example of one component, that is a turbine blade, which is say a structural component, and then you have functionalized that component using several coatings such as bond coat, environmental barrier coating, thermal barrier coating, to provide different types of functionality. So, and this is an essential thing if we want the components to really perform to it efficiently. So if you carefully have a look at, say, just SOEC, for example, here, there is a certain role for each constituent here, right? So be it a hydrogen electrode or oxygen electrode or a barrier layer or a solid electrolyte. So each of these constituent has for sure a different material, and also it needs a different say characteristics in terms of microstructure, thickness, let's say it like that, right? So when it comes to manufacturing them, because these are different materials, they have different requirement, it is not quite straightforward. So if you look at the traditional manufacturing route for some of these devices that I showed you in the previous slide, so basically you prepare the powder or a slurry, and then you tape cast or screen print, you sort of sometimes heat treat or center them, and then you try to also consolidate them or join them on top of each other, so you have a fully functional device, right? So each step basically brings in some sort of complexity, and when it is put together, the complexity is definitely increased to manifold, and particularly because these materials have different uh, properties, especially at high temperatures. For example, the thermal expansion coefficient can be very, very much different. And so the interfaces may have quite different behavior uh, uh, compared to at room temperature. So all these aspects makes the technology deployment uh, slow, because the manufacturing uh, may not be you know uh, quite mature enough. So of course most of these devices are still in use, so that doesn't mean that we do not have the technology there. But we also need to understand that some of the traditional manufacturing routes are also slow in terms of its production rate, like how much material it can deposit per minute. And so that is where I feel that the some of the emerging manufacturing technologies, which I consider as a part of a digital manufacturing theme, can play a role. So for those who do not know, digital manufacturing can be termed as a process where you use digital 3D design information to actually convert raw material directly into 2D or 3D functional components or structural components. And some of the examples are, for example, additive manufacturing, thermal spray, welding, and also maybe there are some other layer-based techniques. So what is common in most of these manufacturing processes, these digital manufacturing processes, is that you have to have a three-dimensional data, which can be a design, or it can be just a robot path that also can be considered as a digital information, a raw material, which can be powder, wire, sheets, also precursor, and some sort of source to consolidate this raw material, which can be some heat source like flame, plasma, light can also be there, or lasers can also be there, right? What is important here is to follow this layer by layer fashion, because then you can actually create multiple layers and into a solid, thick device. And it also gives a flexibility to sort of create gradient if needed, deposit multiple materials, locally change the material composition, and tailor the microstructures. I'll not go into the detail, but this is all possible in many of these technologies that actually I'm giving an example here. And this gives us a freedom sort of, or motivation to try out and explore some of the sort of devices that I showed you, which are not so commonly used or explored for these all of these laser AM or thermal spray methods, right? So I'll basically describe both the laser AM and thermal spray. So for laser AM, which is particularly interesting for creating structural parts. So there are two main methods. One is powder bed fusion. The other one is direct energy deposition. In both cases, we use laser as a source. Both have their own advantages and limitations. But one thing that is very common in both of them is that they both provide possibility to design quite complicated structures. So, for example, the one that you see here is made out of a nickel-based and copper-based alloy. It's a porous structure. So the powder bed fusion definitely gives you more freedom to create a complicated structure than DED, but both of them, compared to the state of the art, allows you to create complex geometries. The material efficiency is also quite high, and you can integrate some of the complicated features like cooling channels in devices like, for example, turbine blades, or maybe the interconnects or metal supports that you're using in various the devices that we just talked. And there is also this technology is also quite suitable remanufacture. So if you believe that there is part that is going to fail, so you can actually just locally repair that instead of changing. So that also provides some sort of sustainable aspect to this. So in general, the technology can actually create complicated structural components for the energy systems, right? But the structural components are often not enough. You need to functionalize them, and that's where the coatings come into picture. And thermal spray is a very versatile technology and has been used for many applications for many years. It is quite new to some of the niche applications in the energy domain, like batteries, for example, or maybe even in SOEC. It's coming into its zone right in the last couple of years or so. But there is definitely a lot of scope here, and the most important thing is that it provides you the deposition rates that are sort of unbeatable with any of the traditional methods, right? So for an industry, it's very appealing. It also gives you flexibility to create coatings out of any sort of material, ceramics, metals, polymers, and their composites. And it's quite mature in many applications. For example, thermal barrier and environmental barrier, the technology has been already very well used and matured. On the other hand, in some cases like batteries, it's still getting uh, its role, right? So I'll present you two case studies of the research that we do. The first one is the use of thermal spray for batteries, and this is a recently concluded a project together with the University West in Sweden, Life Size in Sweden, and Fraunhofer in Dresden, together with UTU. And what we try to demonstrate here is that thermal spray can be a method that can be really looked at uh, f- for applications where the deployment of the technology is really at the edge of whether we can actually create these devices fast and also uh, uh, economically appealing for the industries. Because of the current traditional routes that are there, they are very slow. They have multiple steps there, and it can create also they have their own challenges, right? So there were some preliminary hopes that we had, and we've also demonstrated. Some of the examples are already here, and you can read more about this particular project. We have a public report also available on the EU uh, website there for this particular project. The other case study, and this is more of my own research that I have been conducting since quite many years, and that is how thermal spray can be used, for example, uh, to provide functionality to engines. Now we are talking about deploying hydrogen and ammonia in for combustion in engines. And obviously when we do that, the existing structural components, be it additively or 3D printed, manufactured or traditionally manufactured, would need some modification in its own terms of, say, materials or design. But also maybe there is a scope to provide some additional functionality by adding coatings where thermal spray can also play a role. Uh, because these systems operate at extremely high temperature and or aggressive conditions, corrosive conditions, etc. So you need protection. And there are, for example, thermal barrier coatings or environmental barrier coatings, which are used even in today's state of the art to protect these uh, uh, components from these aggressive environments. And because when you burn hydrogen or ammonia, we do not really know how the structural components gonna react to this kind of new fuel. There is also some sort of challenge uh, on whether the existing coating systems will survive or there will be a need of a different systems, right? And so even here, this whole as a system is consisting of different materials. And so yeah, this is basically the second case study. Now, be it thermal spray or laser additive manufacturing, what is one important point that I would like to highlight here is that for many of the applications that I'm trying to pitch in here, say batteries or SOEC, something similar like that, or even the case where hydrogen and ammonia is burnt in the engines. Um, it is new to both the laser AM and thermal spray, and uh, uh, we are aware of that because it's a thermal process. In many cases, the material system that is actually currently used in some of the applications, for example, batteries, there is lithium there. These thermal processes uh, may not be suitable in its current form. So they need some modification in the process parameters, etc. Right. So there is a lot of work there, and because the process, as we all know, that it can affect significantly the structure and then hence the performance, especially the porosity, grain structure, phase composition is very, very important, which affects your conductivity, durability, or corrosion resistance. So to give you an example, say in one of our research, what we tried, so we fixed the raw material, the feedstock conditions, and varied the process parameters, and you can see like how sort of distinct microstructures you can get. So without getting into the details what these were for, the important message here is that if you can vary the structure so much from one end to other end, you can expect a significant change in the performance. And similarly, in another case, we just fixated the uh, uh, spray, the process parameters, but just varied the raw material conditions, and you can see the same sort of change. So the message here is that it is very sensitive, right? So be it thermal spray here, or I would maybe take one more slide. I don't have it here, but just trying to tell you that the similar effect is also quite evident in the laser AM processes. Of course, the structure looks differently there, but it changes quite rapidly. If so, there is a lot of sensitivity. So it needs, I mean, this both of these techniques needs a lot of control over the process. Now, if you would like to make the transition from lab to really the industries, because both the technologies, because of its high deposition rates and already sort of accepted technologies by industry for various other application, it is quite appealing. But at the same time, there are challenges because of the reproducibility of the microstructures, right? There is a quite sensitive process, and also there are not so many, at least in the laser AM community, there are not so many process experts who can actually do this repeatedly. Uh, so despite the fact that these processes are scalable and for sure compatible with the various industrial needs, because of the reproducibility of the microstructure, there is a bit of a challenge. And this can be tailored and has already been, you know, uh, to some extent solved. So nowadays there is a lot of sort of this digital transition where you try to modify your existing process by introducing some sensors using artificial intelligence and machine learning to sort of automate and control your process so you actually get a very repeatable structures. So so these are the steps that needs to be taken to really make sure that we, and these all these reproducibility related challenges kind of um, say increased by many fold when you're actually trying to use the laser AM or thermal spray or a combination of it to create the whole stack of a system, be it SOEC or the turbine blade coated with thermal spray coatings or a whole battery cell. And therefore these aspects are very important. So at UTU, we are quite heavily focusing on the manufacturing aspect. So we have various processes towards laser-based manufacturing using laser AM, but also other laser processes such as welding, laser surface modification, thermal spray, and we try to connect with industries to make sure that we kind of try to deploy these technologies for different applications. And so, yeah, we look forward for various collaborators, especially in the field of SOFC, SOEC, batteries, which are quite new to us. But we feel there is a lot of promise in these kind of technologies. So in conclusion, I would say when we talk about sustainable energy systems, we should look at the three pillars: the production, storage, as well as the use of it. And then all of these, they require multi-material architectures. And even though the materials that are there, there is a scope to, of course, develop new materials, but I would say that even the state-of-the-art materials can be considered good enough. Despite of that, there is a slow deployment of these technologies. And in my opinion, one of the major reason is the manufacturing. So that is a bottleneck, and we need to sort of solve that. And the digital manufacturing methods like laser AM and thermal spray, just few examples I'm giving. There are many others that can definitely provide a solution that can be scalable and also appealing for the industries. So yeah, I mean, and most important thing in these processes is to mature this process structure relationship. So the last statement is like this advanced manufacturing or digital manufacturing will definitely play a critical role in enabling next generation sustainable energy technologies. Thank you, Faisal.
Thank you, Ashish. A lot of things going on at your end, so maybe we'll connect back to you later on. Right, so if I may invite the last speaker, Professor Ian Froitzheim from Chalmers.
Hello.
Hello.
Yes. You wait a second. I'm trying to get my screen ready here. And sorry, I'm almost ready. Just need to find the share. So now you should be
Yes, we can
my
see
screen, I suppose, right?
Yeah.
All right. So my name is Jan Froitzheim from Chalmers University of Technology, and I'll be talking about interconnects. One slide on Chalmers, if we're talking about collaboration with the Nordics. So we're located in Gothenburg, technical university with about 10,000 students and 3,000 employees. Foundation university founded, we were founded in 1829, but we're different to many other universities. We're not state-owned, but we're actually a private university or a foundation university. So this is a schematic of an SOFC, and you have seen others before today. One SO or fuel cell gives you about 1 volt. So what you do in practice is you connect many cells in series, and what you have then to keep basically the gas compartment separated is the interconnect. So it's separating the gas compartments, manifolding the gas, and also is part of the electric circuit. And this is the same for SOFC or SOEC. That doesn't really matter in this context. So you need something there which is the interconnect, and the most typical used material is iron chromium steels here, so ferritic stainless steel. And why do we use ferritic stainless steel? The reason for that is that the main reason is the similar thermal expansion coefficient compared to the ceramics. And then the steel provides, the steel itself has a good electrical conductivity. It's relatively easy to form and cheap to produce. So, okay, this is stainless, but at the high operating temperature, we're talking about 600 to 800 degrees C or something like that. The steel is not so stainless anymore, but forms an oxide scale. And so we basically get a chromia scale, Cr2O3. And that is good because that protects the steel from further corrosion, it still corrodes, but it corrodes slowly. And the chromia is reasonably conductive. However, it's not a great conductor compared to other oxides, particularly those used in, for example, in the air electrode. So it increases the electrical resistance with time. And it requires a continuous chromium supply. So if we don't continue to supply chromium here at the metal oxide interface, the chromia scale, I mean, we'll start to form iron oxides, which grow much, much faster. So that we need to avoid. Another problem is that we have chromium-6 evaporation. At high temperature, you have this chromia together with water vapor and oxygen forms this chromium oxyhydroxide, which is poisoning the cathode if we're talking fuel cell. So that is a problem, and that's a well-known problem. And the usual remedy against that is use of coatings. I'll come back to that in a minute. I just wanted to briefly show how we do our experiments. This is some images from our labs. So we have 2 labs here that are dedicated for solid oxide cell research with plenty of furnaces. And I'll come show a schematic of those furnaces in a minute, where we can run air or argon hydrogen. And we have about, I think in total it's about 50 systems. And then we have also a lab for corrosive gases, not so super relevant maybe for solid oxide, but then we have also what we call the low PO2 lab, where we can run 100% hydrogen, methane, CO, and so on, and all the more nasty stuff. So here's the schematic of our furnace system. So you see, I mean, as you've seen on the image before, it's basically almost all tube furnaces. So the furnaces here, the samples would be here in the middle somewhere. We have gas inlet here, which is humidified if we want to have humidity. And then we actually humidify it a little bit more than when we need. And we have a condenser here to condense out surplus humidity. And then it goes into the system. And here we have our denuder tube, which we call it. Come to that next slide. That's to collect the chromium that has evaporated. And then that's the outlet here. So the advantage of this setup is we have a very good controllable airflow. If you just have like an open furnace, you don't really know what airflow you have, and your basically humidity varies depending on whether it's summer and winter and stuff like that. So we can adjust that pretty accurately. However, in terms of, I mean, it's more expensive, and also we have much more limited throughput compared to if you have one box furnace where you can put in, I don't know, 20, 30 samples at once. Here's a little bit more detail of the setup we are using. So you have the gas coming in here, left-hand side. Here's our sample. So this is now the tube that is in the tube furnace. And then you have downstream of the sample, you have this quartz tube, which I call a denuder tube, which is coated with sodium carbonate. And the trick with the sodium carbonate is that the chromium oxyhydroxide reacts with the sodium carbonate and forms sodium chromate. So that is deposited in the tube, and then we can just basically remove the tube without touching the samples, replace it with a new one, and then we leach that tube with water, and then we get the chromate solution in water because this is water soluble, and then we can, with a spectrophotometry, measure the chromate content in the solution. Pretty straightforward. So developed that quite a while ago, and yeah, I'm using it quite frequently, and some other labs have also started to use this. To verify this, we used chromia pellets that were weighed before and after the experiment. And so the weight loss of the chromium pellets should correspond to the amount of chromium we find in our solution. And that actually works. And here you see a plot of uncoated 441. And you see, I mean, you don't even see the error. I mean, here you see some error bars. But so the reproducibility of this is very good. So now we can measure chromium evaporation, but we still need to do something about it. And that's where the coating development comes in. This is a lot of this work has been done together with, or nowadays it's a LEMA, formerly Mesandic Materials Technology. That is an image of their coil-to-coil production line, where they can basically, coil with kilometers of steel can be run through this production line, and is coated and then afterwards stamped into interconnects. So, okay, we want to minimize chromium evaporation. How do we do that? This is, I mean, if we have the typical steel used as the iron chromium, there's also like maybe 0.5% of manganese or something in the steel. So you get something like, then you get an oxide scale that consists of the chromia scale I mentioned before, or on top of that, there will be a chromium manganese spinel. That will give you somewhat lower evaporation, but it will be still too high. So what you can do is you can apply, for example, cobalt coatings. That's what we have been working a lot on. And particularly, we use very thin cobalt coatings, like about 600 nanometers. And then instead of this chromium manganese spinel, you get a cobalt manganese spinel. So the idea is to block chrome evaporation when you have this cobalt manganese spinel. And this is a plot of chrome evaporation here as a function of time for up to 3,000 hours, or for a little more than 3,000 hours. And you see the uncoated material up here, and then here for more than 3,000 hours, and that was 850 degrees C, so pretty challenging temperature. The evaporation rate is reduced by a factor of, well, it's actually more than a factor of 10, it's more like it's close to a factor of 50, because at that point we had uncoated edges that gave us some contribution. So this worked very nice. Here's the TM image of the oxide scale with this cobalt coating after 3,000 hours. You see here the fine-grained chromium scale, down here the steel, and out here is the cobalt manganese spinel with some iron. And if we look with the EDX a little bit closer here, we can see here this line scan. We see, so here's the chromium scale, and then we move outwards. You see cobalt manganese, but there's hardly any iron, any chromium out there. And so this is after 3,000 hours, so the coating is still performing very well. Then we wanted to increase the corrosion resistance. To do that, we combined this cobalt coating with 10 nanometers of cerium underneath the cobalt. So you get this combination of cerium and cobalt. And again, here's this TM image of the oxide scale. And here is with adding 10 nanometers of cerium, same magnification, same exposure conditions. You see that this chromia scale is roughly 1/3 to what we had with only cobalt. So the cerium slows down the chromia growth quite significantly. Okay, this was, 3,000 hours was of course nice, but you want to operate your stack much longer than that. So this is data obtained that was measured for up to 40,000 hours or 38,000 hours on 441 steel, 800 degrees C. And you see here the different batches, and you see basically what we call as parabolic behavior. So basically the oxide scale, as the oxide scale grows, it becomes heavier. That's a mass gain we measure. But over time, this is not linear, but it slows down in a more or less parabolic fashion. That's basically good, and that's what we want. So mass gain looks good. What we don't want to see is something when it continues like this and then jumps up, because then we start to form iron oxides. And that's what is called breakaway corrosion. But in terms of chrome evaporation, we couldn't measure for 40,000 hours. We didn't want to. So what we did instead, we measured initially those data you had seen before. And then we took those samples after 38,000 hours and put them back into our setup and measured again. And you see there initially they're higher, but you see that drops within, maybe 200 hours or something, and we know what is happening here. And then it basically goes back to the same values that we had here initially. So even for these very long exposure durations, the coating performs very stable. And as the interconnect is part of the electric circuit, it's also important to keep the resistance of the coating in mind. I mean, we could coat with alumina, for example, and the corrosion resistance would be fantastic. Chrome evaporation would be no problem, but the resistance would be way too high. So here's the area-specific resistance as a function of temperature here, and you see it's slowly increasing, roughly following the same parabolic kinetics we've seen before, but 35 milliohms after 40,000 hours is considered to be an extremely good value. So this was an example of our coating development, and this is commercialized by Alema and used, for example, in Doosan has a 50 megawatt factory in Korea, where they're, for example, using these coatings. Or at least I suspect they're using that, or at least they bought them. If we talk about, now I want to talk about something else, and that is a dual atmosphere. And the point is that if you have you interconnect as part, it sees both the air side, or the atmosphere, the steel is exposed to air on one side and the fuel atmosphere on the other side. And that turns out to be a bit different to just having air on both sides or fuel on both sides. So in order to investigate that, we developed this sample holder, which actually we used or modified the design from Montana State. So you have this block here of material, and you have a gas tube, a hydrogen tube here. So the hydrogen goes through here. You see the gas channel down here, and then continues all the way and comes out here. And so the sample, so you see here, here's a gold seal, then the sample comes here, and then you come your clamping ring. So this sample here will be exposed on the backside that we don't see right now, with hydrogen, while on the outside here, it will be air. So this sample is exposed to dual conditions. And the hypothesis is that hydrogen from the fuel side diffuses through the sample and affects air side oxidation. And as a reference, we have another gas channel here on the back side, or you don't see that. There are 3 more slots where you have 3 more samples, and those samples are have air on the inside and air on the outside. So we have a reference case where the sample is exposed to air on both sides. And so this is after 1,000 hours visual inspection, 600 degrees C, so relatively low temperature. You see we have a relatively shiny metal surface, so everything is fine in single atmosphere, so air on both sides. However, if you do dual atmosphere, we get breakaway corrosion. Here you see like quite large part of the sample is covered with what turns out to be thick iron oxide. I'll show you later. So we repeated this experiment and got pretty much the same result here, you can see. And well, you can argue, well, maybe this is just starting and it would have started gone. I mean, you have some spots here, right? So maybe this would have happened in single atmosphere as well. So we let this run for 3,000 hours, and you see the same spots here. Nothing has happened here in single atmosphere, but in dual atmosphere, the sample looks a lot worse. So we showed this. A lot of people criticized, yeah, maybe you have a leakage or something like that. That was one of the standard critiques for this. And to those people, I like to show this slide. When we did our first experiment, this is the stainless steel pipes, 316 steel, that lead to the sample holder here. So this tube had air on the inside, this tube had fuel on the inside. This is like 1 millimeter stainless 316 steel, and you see immediately this massive difference. And this is like 20 centimeters from any connection. So there is clearly, this is not leakage. This is going through the steel. So yeah, to summarize, basically in air, if we have air on both sides, we get a thin protective scale. And the oxide scale is, yeah, we're talking about a couple of 100 nanometers, basically. While if we have fuel on the one side, it's the air side that is affected with this fast-growing iron-rich oxide. And then the sample looks like this, and you get like, what is it, 30 microns of oxide scale or something like that, depending a little bit how long you run and so on. But so it's a massive difference. So instead of this thin protective chromia scale, we get non-protective iron-rich oxide. So, and then the question is, of course, what is going on here? And in a simplified manner, we can say basically, when we have this chromia scale, to maintain this chromia scale, we need to make sure that we can supply more chromia to this metal oxide interface compared to the amount of chromium we're consuming. If this is the case, if we can supply more than we consume, everything is fine and we keep this protective scale. However, if the consumption gets larger than the supply, we deplete our chromia scale in chromium and we start to incorporate iron, and then we get this fast-growing breakaway morphology that looks like this. So generally speaking, so hydrogen is somehow affecting this equilibrium here between consumption and supply. And figuring out what is exactly going on is still partly ongoing problem. Yeah, I'll come back to that. But we looked at a lot of parameters that influence this. For example, the temperature dependence, the effect of pre-oxidation, how the sample thickness, and so on and so forth. So I'll just show some examples. One interesting example is the temperature dependence. For example, at 500 degrees C, with pre-oxidized samples after 2 weeks in dual atmosphere, you see the oxide scale is very thin and protective, everything is fine. If you increase the temperature, things get worse, and you get these oxide islands of thick oxide. 600 degrees C is uniform, but it's uniformly thick. And that's basically the cross-sections you have seen before. So then it's a disaster. And then, interestingly, when you increase the temperature further, you get more protective scale again. And at 800 degrees C, you have a completely protective scale again. So the most severe dual atmosphere effect is observed at 600 degrees C. And that is a little bit unusual. Usually, it's like the higher the temperature goes, the worse things get. And if you go down in temperature, things get more manageable. But here, this is not the case. So this suggests that the hydrogen affects grain boundary diffusion paths in the alloy, or that's at least what we speculate. I don't really have the time to go into all the details, but the grain boundary diffusion contribution is much more significant at 600 compared to 800 degrees C. And yeah, and at 550, basically it's too cold for much to happen anyway. So we looked at the pre-oxidation as a parameter. This is basically samples. We had samples pre-oxidized for different times. So this is the different pre-oxidations here, and this is before exposure. Nothing happened so far. And after 24, you see the non-pre-oxidized samples already dead, while the other samples survive. And then if you go longer, for like after a week, the shortest pre-oxidations are dead, while the long ones look okay. And that's basically continues. So you get a somewhat, I don't know if it's a straight line, but you get some kind of line. I mean, we managed to break this 280-minute sample eventually after 5,000 hours. But there is some kind of, there's a clear correlation there. Basically, we can summarize it that way. We looked at the effect of sample thickness, and somewhat unsurprising, like if you thinner the sample, the easier it's for the hydrogen to get through. We get this most severe effect, while the sample, if it's thicker, it's less severe effect. So to summarize, 600 degrees C is the worst case. Pre-oxidation helps, gives us less hydrogen ingress. Thinner samples are more affected, but the effect is not super strong. Cold working, so for example, grinding helps, gives us higher chromium diffusion. And the humidity on the fuel side, I mean, if we have dry hydrogen on the fuel side, that is more severe. Then the question is, what is going on here? I mean, from basically mechanistic point of view, there you can make up all kinds of different hypotheses. What is going on? This is basically the one that is mostly found in the literature. That hydrogen is incorporated in the oxide scale, and the oxide scale grows faster. And this is clearly disproven by because whenever the oxide scale is protective, the oxide scale thicknesses are pretty similar, if not. Maybe it's the other way around. So you can't compare thin chromium scale to a thick iron oxide scale and say it's growing faster. Chrome evaporation, we looked into that. I mean, we love chrome evaporation, but it doesn't really explain this. We looked at other things like sigma phase formation, hydrogen releasing chrome activity. This was something that we postponed or thought for a while might be the case, but we have also thoroughly disproven that. So in a way, maybe most likely hypothesis right now is that hydrogen affects the chromium diffusivity, in particular at the grain boundaries. That's what we believe, but we don't really have full evidence right now. I think now I'm 18 seconds over time, if I see it correctly here. So this is basically what I wanted to show you. Now I need to find my teams again, but I'm basically done with my talk.
Thank you, Ian, very much for your presentation. We have got 7 minutes for Q&A. I can see there are already some question up there. So one of the question, I think it is for Ashish. Ashish, do you want to answer a question from Adnan?
Yes, yes, of course. I was typing it, but maybe it's best to just answer because it's a bit of a long typing there. So yeah, your question just for the audience is that from an additive manufacturing perspective, how do we control the porosity and other microstructure defects in cathodes and anodes while maintaining mechanical stability and long-term corrosion resistance in high temperature energy systems? And you're also asking if there are any studies. So I just want to clarify here that so what I showed you here when these cathodes and anodes, and these were for the battery system that I actually explained. So those were actually coated using a thermal spray method, right? Although we did try with laser DED. So there are a bit of a challenges when it comes to doing the laser DED or laser powder bed fusion, especially if you go into the melting mode, because most of these materials are, they're non-metallic, they're ceramics or ceramides, and they're prone to crack due to these high cooling rates. But if you, of course, there is a way around it. If you operate your system in a sintering mode, then you may be able to still do it. But on the thermal spray side, yeah, okay. What about gas turbines? I'll come to that also because there was another question here. But for the batteries, that's what we use, thermal spray. And there, if we talk about how do you control the porosity and etc. So of course it is not like, you know, as if you are designing it in actual 3D printing case where you design the model and then you have a specific pore size and shape really defined, and then you get that in the process, in the part when you print it. So in thermal spray, that's not the case. There is a bit of a randomness there, so that you cannot change. That is how the process is. But obviously, because there is a lot of studies, there are a lot of work which kind of taught us that even if at a random there is a randomness, but even in that randomness you can still control, not to one single pore but maybe to some quantity, the size range of the pores. And in one of the paper that I did together with University West, we kind of showed like how you can control the size of the pore starting from few nanometers to micrometers to, you know, tens, more than 10 to 20 micrometer range, by just tuning the process parameters. And in process parameters, I mean the both the feedstock, because there you can switch to precursor, or you can go to the powder, and that can actually change the length scale of the pores. Also to some extent shape, but you don't get the freedom to have one pore design as you get in the laser AM. That is actually still sort of my wish, that if we can actually do that, because so that is more of the material material combined together with the lasers that we use, the kind of the challenge that we have. So that is
That's
about
wonderful.
the, yeah.
So there's another question, Ashish, for you from Ian. What is the maturity of printing SOC by additive manufacturing?
So I would say here, additive manufacturing is a very broad domain. There are several methods that come into it. So the ones that I talked, laser additive manufacturing is one of this. So if you talk in general about additive manufacturing, say binder jetting is also a part of it, right? And then there are other methods such as this nanoscale printing, etc. So depending on the process, the maturity varies. But I am more interested in the AM processes that that has high deposition rate, and there the processes like binder jetting or laser based AM such as laser sintering or laser melting come into picture. And I think the maturity is maybe a little bit towards low when we talk about the functional layers, but it is certainly very appealing when you talk about the interconnects or um, the metal support, and also if there is any other structure around these SOCs. So I know that at least an Estonian company is very well sort of exploring this particular option
Okay.
to use AM for the not for the functional layers, but the other things which are made out of metals.
Okay, thank you very much. So I think there is a question from Rafael for Ian. Is the dual atmosphere problem also occurring for electrolysis, or is it limited to fuel cell operation? You're on mute.
No, I'm muted. No, that's basically. I mean, that's basically the same for electrolysis. Then I mean, it always depends on. I mean, the atmosphere plays a role, and I mean your SOFC inlet atmosphere compared to SOFC outlet and your SOEC inlet and outlet. But I mean, they're mostly overlapping, right? And then so the problem occurs in both cases.
Thank you. One question for Rafael from me, if you don't mind. You did show about the temperature and the voltage plot for high temperature. So not many literature discuss about the pressure range. For various sector, say nuclear or or maybe petrochemical, there are flow rate of steam happening. So do you think residence time of the steam in the system at certain pressure have any influence?
You mean the pressure of the steam has influence on the voltage, or is
yes.
it?
No, in terms of electrolysis.
We'll have an impact, and you can calculate this impact from the Nernst equation and so on. And so what we did, it's not published, but we did some investigations on the ammonia, if there is any gain, like, because you can, like, instead of compressing the hydrogen, you can compress the steam. But you also limit how much heat integration you can have sometimes, because the temperature will be higher. So just say that you save more energy by having like the steam at high pressure compared to the compression of the gas. But if you are paying also the heat integration, then it could be that it's at zero sum. So I would refer to like calculating to the Nernst equation. If you're curious, I have not seen like a lot of plots being generated on that.
Indeed, yes. Thank you. One question for Ian. You mentioned about 40,000 hours of testing. So I believe these are continuous testing you have done.
Yes, or I mean, in that case, what we did is those samples were the 40,000 hour samples, where I mean, you see those were I mean, they were discontinuous in the sense that there you took out the samples after every few thousand hours to weigh them and then put them back in. So they saw a few thermal cycles. So each data point is basically one thermal cycle. For the 40,000 hour samples, and those were also not done in a tube furnace, but in a box furnace with like lots of other samples, and that's part of the reason why we had initially this higher chrome evaporation.
I see. Other question, you did mention about cesium layer in between
Cerium,
to minimize,
yes.
Sorry, cerium, yes, layer to
Yep.
reduce the oxidation and corrosion. So do you think for a steam electrolyzer, we could consider on a metallic substrate, create a cerium layer first and then maybe do rest of the deposition later?
Yes.
Because we are observing some oxidation of iron oxide around 5 micron thick. And
you said you had a metal substrate you had, or?
Yes, stainless steel.
But I mean, in terms of are we thinking like metal supported cell or?
Metal supported, yeah.
Supported cell, yes. Okay, and you have some. You have some foam structure, or what do you have?
It is over the porous wall, the iron oxide layer about 5 micron is building up.
Yes.
And that, of course, will reduce, means will have electrical resistance. So do you suggest to consider a cerium layer?
Yes. I mean, cerium is my favorite element. No, it has. I mean, also like cerium, lanthanum. Those in the high temperature corrosion world, they're known as reactive elements. They are. I mean, even in very small amounts, they have a very significant effect in reducing oxidation rates. And if you have like a porous metal structure, as you have in a substrate, where you have like an awful lot of surface area, things can corrode very nasty. I know we had an EU project with DTU for, I mean, quite some years ago, where we looked into metal supports, and their impregnation with some reactive elements had actually quite significant effect in reducing that. So yeah, that I think is a good idea.
That's great. Thank you. Any other question before we close the session today? If not, then I think we can call it a day. Thank you very much for your time today. I'll send you email with some other information and slide if possible. And also, if you want to register for next event, please feel free to do so. Thank you very much.
Thanks to all the speakers. Thanks so much.
Thank you very much for the opportunity.
Exactly. Thanks for the invitation. Bye-bye.
Bye.